One of the most interesting things about this discovery of energy and how they relate to frequency and wavelength for light is that when we take element in their gas phases, we put them in like a light bulb like this, and then we heat them up or we connect them to electricity. We notice that they start to glow. You've seen this in many types of advertisements on the freeway, that they use this really colorful light to form these letters. Okay, so in this particular case, we're using it to form these noble gases. Another way to see this is we can do something called a flame test, where you can take a flame, like a Bunsen burner, and when you put different elements into the flame, you'll notice that the color of the flame changes. So for example, here barium has a purplish color, whereas calcium has an orange color, and potassium has a reddish color, zinc has a yellowish color. So this is just a color specific to that particular element. So the question then becomes, how do these elements generate light of different colors? Well, the way this works depends on how the electrons are arranged in the atom of these elements. So we have to kind of go back to our picture of the atom that we looked at some time ago. Remember that the atom has a nucleus in the center, and the nucleus contains protons and neutrons. In this case, the neutrons is not relevant to our discussion, so we're just showing proton right here. And then remember that the electrons, which are the negatively charged particles, are moving around in the atomic space. Now, what we learned at the beginning of the 20th century is that it turns out these electrons are located in specific parts of the atom. Like, they're not allowed to be found anywhere in the atom. They have to be located in these specific parts. We call these parts of the atom where the electrons are found shells. The shells are numbered, so the symbol that we use for the shell is N, starting with the lowest one being N equals 1. So that's the N equals 1 shell, and then the next one is N equals 2, and so on. The lowest shell is what we call the ground state. So that's the most stable position. It's kind of like thinking about if you have a ball and you let it go from your hand, then it's going to fall to the ground, right? And so that's why it's called the ground state, because that's where the ball wants to be. In this case, the ground state is where the electron wants to be. That's the most stable state for the electron. It doesn't mean that you can't move the electron to a higher state. In fact, like a ball, I can take it and move it up, right? And when I do that, I need to put in energy. I'm the one putting in energy to the ball to move it up to a higher level. Same thing here, the electron could move from a lower N to a higher N as long as you put energy in. And when you do that, we call it an absorption. So the electron has absorbed energy, and it moves from, in this drawing right here, level 2 to level 3. That energy can be absorbed in the form of light. It could also be in the form of electricity, and that's the reason why we're discussing this, because the electricity comes in to this gas, and then the electrons absorb those electrical energy. Now, what happens in the gas bulb is as follows. So at the beginning, before you plug in the gas light bulb into the electrical socket, everything is just in the ground state. All the atoms, all the electrons. When you connect it to the electricity, all those electrons get excited. That's the term we use. It just means that it's moving from that lower to higher shell, or N value. It's sort of like a ball. When I move it up to the top, it's not going to stay there unless I keep it there. But if I let it go, it's going to want to fall back down. So the same thing happens to the electron. When you let it go, it's going to fall back down to the lower level. Now, when a ball falls down to a lower level, to a ground, you hear a sound as the ball hits the ground. That's the energy that's released by the ball when it hits the ground. So the same idea here, when the electron goes from a higher to a lower shell, it releases energy, except that in the case of the electron, the energy is released in the form of light. So we show this little wavy line to represent that light is being emitted or released when the electron falls back. And that's the light that we see either in the flame or in these gas bulbs, right? So they all have different colors because that's specific to the electrons in that element, okay? So you can actually represent this using a diagram like this, what we call an energy diagram, a one-dimensional axis, right? So it goes from low at the bottom to high at the top, and it's just an axis of energy, okay? So the bottom is where our ground state is, so we're going to be at the lowest level of energy here. And then when we start, like in the case of the example that I was just showing you this electron starts from level 2 and it goes to level 3, for example, right? So you start from level 2 and you jump up to level 3. Now in this particular drawing, it jumps all the way to level 6. How high it jumps depends on how much energy you're putting in. So if the electricity is putting in a lot of energy, then the electron could jump much higher. And if it's not, then it's going to jump much lower. But in any case, once it goes up to that high level, let's say it goes to level 6, it wants to eventually come back down to level 2. So when it comes back down to level 2, it's going to release that same amount of energy that it absorbs from electricity. So that is released in the form of light. So this arrow right here is colored purple because the light that is being emitted is a violet light when you go from level 6 to level 2. And this is specific to the hydrogen atom. For example, if the light is absorbed and it jumps to level 5 and then it goes back to level 2, then the light that's being emitted is a blue color light, okay? So this diagram basically just shows you how different color light is being emitted as a result of the electron falling back down. Now, one of the patterns you notice, hopefully, is to connect this back to the energy of light and the color, right, and the wavelength. So notice that this is red, this is green, this is blue, and this is violet. And remember that that energy is the highest for violet. Remember that violet is on this side, which is higher energy because it's higher frequency, shorter wavelength. Red is on this side, which is longer wavelength and shorter frequency, so it's less energy. So keep that in mind when you're looking at this, because what this diagram tells you is that the energy that you observe because of that transition is visible from the color that we see from the light that's emitted. So in this case, if a red light, that means it's a jump from very close or neighboring levels, right? Neighboring shells. Whereas if you get light of higher energy, that means that it's going through a bunch of different levels before it gets to that final destination, okay? And so here's a question on that concept, just to kind of think through it a little bit. So it's asking you which of the electronic transition that's shown results in a light wave with the shortest wavelength. So then what you want to think about is short wavelength corresponds to high frequency. High frequency corresponds to high energy. Okay, so going back to the discussion we had earlier about Planck's equation. So we want a light wave that has the shortest wavelength. We're looking for a transition that gives me the highest amount of energy, okay? So highest amount of energy would be the one that goes through the largest gap in the transition. So that must be this one right here, okay? Because that one has the largest gap, right? Everything else is less than that distance. What about a light wave with the shortest frequency? Well, shortest frequency means least amount of energy. So then I'm looking for the shortest arrow here, and that would be this one, okay?